Hi and welcome back to the second clip in the acids and bases series for A-level chemistry. In the previous clip we looked at the acid-base pairing of HCl as it reacted with water and produced an acidic solution. And so in this example we're going to again look at HCl, but this time we're going to attempt to calculate the pH of a solution that will be formed as a result. Now, in the previous one, we understand that HCl is a strong acid, which means it's going to completely dissociate its hydrogen ions into solution. So if we were to start with a 0.01 moles per litre solution, then we would expect that after its complete dissociation, we would also generate a 0.01 molar solution of H plus ions. We can then use a calculation to establish what the pH is of that solution. And pH is a relationship of the hydrogen ion concentration, and it's calculated by taking the logarithm of the hydrogen ion concentration to the base 10 and changing the sign. So using a calculator, if you were to input the value of 0.01 and then take the log of that value, you will get a calculated value of -2, which if you then change the sign of by the minus sign there, would then change the pH of that solution to +2. So a 0.01 molar solution will end up having a pH of +2. And it's worth trying to practice on your calculator, depending on which type of calculator you have, to make sure you can enter the key presses in the correct order for that. So 0.01 molar solution will give you a pH of 2. As I say, this is a logarithmic scale. And logarithmic scales are useful when you are potentially looking at a wide range of values that you may be working with. So in aqueous solutions, the concentration of hydrogen ions can be very small, perhaps down to the 10 to the -14 moles per litre concentration, so very, very small, all the way up to 2 molar solutions for typical lab-based HCl solutions, for example. And so a logarithmic scale takes that wide range of numbers, often numbers which are very, very small, and turns them into more user-friendly numbers. So 0.01 is potentially not particularly user-friendly, but 2 is a much better number. And so this pH equals minus log base 10 of the hydrogen ion concentration equation is a way of taking those wide-ranging numbers and giving us numbers that we can more easily use. And typically pHs will be between 1 and 14, although it is possible to have values outside of that range. If we had a pH and we wanted to go back to the hydrogen ion concentration, if we had been given the pH, then the inverse of the logarithm is to take a pH value and put that to the power of the 10. So 10 to the power of minus pH. So again, using your calculator, you would ultimately have a number of 10 to the -2. That, when you calculate it through, would take you back to your original 0.01 moles per litre. And so you can go either, say, from hydrogen ion concentrations to pH, and vice versa, from the pH value back to the hydrogen ion concentrations. This works directly for strong acids, whereby you get complete dissociation. In this example, it was a monoprotic acid, which meant that we had one HCl molecule dissociated in water to produce one hydrogen ion, and so we just used the concentration directly. If it had been sulfuric acid, for example, so H2SO4, then we would have had to double up the hydrogen ion. So if, for example, we had H2SO4 of the same concentration, so 0.01 molar of the sulfuric acid, because that would have produced 2 hydrogen ions when it dissociated in solution, the hydrogen ion concentration would have been 0.02 moles per litre. And so when you put that into a pH calculation, you wouldn't get the same value. That would be a slightly lower pH than pH 2. And for sulfuric acid, if we were to do that calculation, so if you were to again practice on your calculator, putting the numbers in, the pH will come out something in the region of 1.7, rounded to 2 significant figures. In this specific example, slightly stronger than the pH 2 of the HCl. But this gives us a way of calculating pH values from a known concentration. And we know that we can then go backwards and forwards using those concentration differences. Because it's a logarithmic scale, you may remember from GCSE that a factor of 10 change in the pH, in the concentration, so from 0.01 to 0.1, or going the other way to 0.001, you would change the pH by a unit of 1, depending on whether or not you've gone up or not. So we know from GCSE that if we had changed that concentration to 0.1 moles per decimeter cubed, for example, that has increased by a factor of 10. And at GCSE is a common question, and again, not necessarily at A level, but the same answers would be true. This would probably have a pH of 1 if we had a monoprotic acid. That factor of 10 change in the concentration here is leading us to a 1 unit change in the pH value. And so, as we say, that's the calculation for these. This relates to strong acids. In the next example, we will look at how water can influence the pH of a solution, and something specifically called the ionic product of water. And then we'll go into calculating the pH of weaker acids, which is a little bit more complex than simply inserting a singular value into an equation. We have to use equilibrium constants and some associated chemistry there. So I'll see you in the next few clips, but thank you for now.